All right, guys, welcome back. It's been a little bit of a break, but we're going to continue on with our discussion of BGP. Actually, in this case, we're done with BGP. It's been so long, I've forgotten where we are. We're doing optimizing routing, and what I decided to do in this particular lesson was skip a couple of lessons because I thought this one was probably more appropriate to start off with our discussion, and then get into some of the details like the actual configurations and so on when we get into routing protocol failure detection and bidirectional detection, forwarding detection, which will be our next couple of lessons. And then we'll wrap up our optimization by doing EIGRP, IPFRR, and OSPF LFA, which, by the way, we're going to introduce in this particular lesson here. So in our next section, we're basically just going to talk about routing protocol event propagation and focus on what the effect of routing protocol event propagation is from a perspective of convergence optimization. Specifically, what can we change in the event propagation process that can affect the overall convergence process? Now, previously we did talk about, some of the different options that we have for reactive versus proactive optimizations. OSPF, a loop-free alternative, for example, which is very similar to having something like a successor / feasible successor that we have with EIGRP, prefix independent convergence, MPLS traffic engineering fast reroute. We talked about a lot of these, and I'm going to end up adding essentially our discussion, which is mostly lecture today, to this document, since it is relevant and kind of related to what we've been talking about in the last few lessons. So the first thing I think that we should do as part of this discussion is kind of quickly review what does it even mean with this term event propagation time, and take a look at what are some of the optimizations that we can do in EIGRP or in OSPF or BGP to help lower that convergence time by changing specific parameters. I mean, in the past, we've certainly talked about the benefits of scoping queries within the EIGRP topology by using stub routing features. We talked about using special area types in OSPF. We didn't really get into too much of the event propagation and convergence manipulation in BGP, because in reality with BGP, we're typically dealing with TCP convergence as opposed to its own layer 3 protocol transport, which is what EIGRP and OSPF has. All right, so there are 4 different variables that are in essence what we need for convergence. And if we look at this document here, we can kind of see what those 4 major factors are. How long does it take for me to detect the failure? How long does it take for that change to propagate through the network? How long does it take for me to recalculate my new databases, my new routes, etc.? And then finally, how long does it take for me to actually update the FIB, the routing information base, and all of my forwarding engines, whether they're centrally located or based on the line card itself. All right, so we're still going to kind of think about this from that particular perspective, but we're going to take a look at other options that we have in this particular case outside of what the standard options we had before, in our basic design, right? Things that are built into the protocols themselves, like query scoping, like creating these summarization boundaries, like doing special area types, and so on. So those are the things that we will definitely discuss. All right. So those 4 variables, like I said, how long is it going to take for me to detect the failure? How long did it take for me to tell everybody that there was a failure? How long does it take me to recalculate my databases? And how long does it take me to actually install those particular changes? So the event propagation period, or what we're trying to manipulate here, is in essence the second of these particular variables, right? How long does it take for me to tell everybody else? That's the whole idea of event propagation. Now, depending on what type of routing protocol we are going to be using, it's going to be different. Right? With EIGRP, for example, we're going to be talking about if I have to send a query or if I need to get a reply. And that's going to be dependent on whether or not I have the stub routing feature configured, whether or not I have a feasible successor. I've designed in some sort of feasible successor in the topology. If I do have a query, how long is it going to take for me to get the replies back from my peers and from their peers and so on, those kinds of things. We talked about stuck and active, and you can go back and review the information in the EIGRP lessons to be able to kind of talk about the stuck and active query process, stuck and active reply, and so on. In OSPF, we're talking about flooding procedures, what is the scope of the LSA. If there is a topology change within one area based on my ABR configurations, or if I'm bringing routes in from an external domain, my ASBR configurations, am I providing for summarization? Have I configured summarization? And based on that, then what is the scope of the flooding of those link state advertisements from that perspective? All right, so we talk about in OSPF being able to limit the scope of topology change notifications by using special area types, stub, totally stubby, not so stubby, totally not so stubby, and so on. But we're going to get into this in more detail by looking at the actual timers, looking at how we might be able to do group advertisements in OSPF as opposed to flooding out LSA advertisements as soon as an event occurs, those kinds of things, all right? And so we're going to dig, I suppose, a little bit more in detail than what we've talked about previously in these particular topics. With BGP, it's really just about managing the update and withdrawal process. We can do prefix prioritization, BGP pick, either edge or core, like I said. But again, we need to take a look at case studies where we might want to implement these particular functions, all right? So let's say, for example, in our particular case, let's look at EIGRP as an example. EIGRP is a relatively easy protocol to work with. It's actually one of the easiest protocols to tune because event propagation is really going to be bounded by the size of the query domain that you've established. And we know that based on the dual algorithm, based on the EIGRP topology design, if I can build in not only my successor paths, but I can build the topology in a way that I have feasible successors, then I don't even really need to do a recalculation of the domain itself. I can simply use those other routes. That doesn't mean that changes don't have to be propagated, but we're not going to be losing the routing information based on that particular requirement, based on that change requirement, all right? Now, we talked about all of this a bunch before. We were talking about feasible successors, and we even had some lessons specifically on how to deal with EIGRP stub routers, how to set up summaries. But what was the one thing about EIGRP that made it so much easier to work with than a lot of these other routing protocols? EIGRP is a flat architecture, right? We don't have an architecture like a spine and leaf architecture that we have with OSPF, where we have a very specific topology that we have to create these boundaries, if you will, where we can implement flooding, propagation limitations, and summarization boundaries. In EIGRP, it's arbitrary. We can, in essence, implement the stub feature on any router. We don't have to make an area a stub, for example, like we do in OSPF. And we have the ability to manage the domain very easily because, again, the network itself is completely arbitrary. Now, I'm going to add a few things to our document here from our previous lesson because I want to make sure that we have the details here. But from an EIGRP perspective, all right, the first thing that we say is that we say that the event propagation is bounded by the EIGRP query domain. All right, now what that means is that the smaller the query domain, all right, the smaller the query domain, the less devices the events need to be sent to. All right, probably not a great sentence, but anyway, you get the idea. Now, how do we create that query domain? Well, first of all, it would depend on the physical architecture, right? We certainly would not want to configure a feature like stub routing on an EIGRP transit router. a router that would provide alternate paths to a destination. We would only want to necessarily configure this stub configuration on stub routers that are not going to act as a transit path in the topology. But a lot of our major designs that we have today include that design, right? DMVPN hub and spoke topologies and so on. All right. Now, what are some of the other elements that we can do to in essence design in this quicker event propagation? We need to engineer in the design feasible successors. All right. Now that means that for a feasible successor route to be qualified, first of all, it would have to be a loop-free alternate path. And we verify that loop-free alternate path status by saying that the reported distance of that feasible successor is less than the feasible distance of the current successor. Okay? And that may not inherently be built into the design by default. It certainly is something that can be configured, right? It's certainly something that can be configured, but the point is that it may not necessarily be by default part of that design, just simply because of the circuit paths that we have and the metrics that might be in place. Even though we know that there is no loop, EIGRP may not be aware of that because of the overall physical architecture. So we could change values, we could change bandwidths, or we could change delays. We could in effect adjust the overall path metric or the reported distance of a particular path to make sure that we're engineering in this this feasible successor. All right, and you guys don't understand from our previous discussion, if I have a feasible successor and my successor path goes down, it doesn't require a reconvergence event per se. I mean, we will have to eventually propagate the overall topology change, but from a routing perspective, from a forwarding perspective, we simply go ahead and start using that feasible successor as our successor path. The other option is to engineer in stub routers. All right, we could do like stub connected, summary, receive only, there's etc. Right? There's several others. Right? There's a redistributed, receive only, connected, summary, and what am I missing? I'm missing one. Let me think about this. Receive only, stub connected, summary, receive only. I'm missing one. 1, 2, 3, 4. There should be 5. Stub connected, summary, receive only, redistributed. I might as well put it in here. Redistributed. Okay. Oh, and static. I also forgot static. All right. So in any event, we have the option of identifying different types of stub routers. Now, those options that you see in the parentheses there don't really affect the query domain because there's two aspects to setting up a stub router in EIGRP. Who am I going to send a query to in the event of a topology change, and then also what is that stub router going to provide upstream to its neighbor routers when it's advertising prefixes to its neighbor routers. All right, and we talked about this. This is not anything new. It's certainly something that we've talked about in quite a bit of detail actually in our EIGRP lessons. The other option is to engineer in summary boundaries. Now this does require, of course, hierarchical addressing, good address design, and network placement, because we want to make sure that we have nice clean boundaries. But the nice thing about this from an EIGRP perspective is that we don't have to worry about this from a from an overall topology architecture like we do in OSPF with regard to the fact that we can only summarize on an area border router or an autonomous system boundary router, right? In EIGRP, we can summarize out any interface in any direction, okay? The basic point here is that I have a route installed to a particular destination, And either I lose the route or I lose the neighbor, and then the route goes into some sort of active state. That's part of the EIGRP process. Now the active state is, in essence, when I lose my successor route and I don't have a feasible successor, and I need to then in turn go out and search for a new successor. Now I might have an alternate path, right? We have routes in EIGRP that qualify as successors. We have routes that qualify as feasible successors. And then we have other candidate routes that just simply have to be verified in the event that there's a failure because they don't meet the feasibility condition to qualify them as a feasible successor. So if I lose my successor and I don't have a feasible successor, that's when I go into the active state. I send a query to all of my other adjacent neighbors and I say, hey, do you guys have an alternate path to get to this particular destination? Now, the easiest way, as I've already mentioned a couple of times, to solve this event propagation problem in EIGRP is to basically never allow the route to go into an active state to begin with. And those options that I listed here on the slide, on the screen here, are the options that we have. Engineer in a feasible successor. If I have a primary path and I have a pre-calculated backup path, when the primary neighbor goes down or the primary path goes down, I don't have to propagate any event because I can simply start using the backup path. So if the router never goes into an active state and I immediately switch over to the feasible successor, then that means I get sub-second convergence. And that's why I often tell people that EIGRP from a design perspective, if it's designed correctly, will actually converge faster than its OSPF link state counterpart. Because of the ease of implementation from a feasibility successor condition. Now, in the case that EIGRP is not subject to either recalculation times or the routing protocol installation time, the actual fib update is going to be very, very fast, assuming that we're doing some sort of IP fast reroute with EIGRP. Now, we will actually talk about EIGRP IP fast reroute a little bit later on. That's one of the topics that we didn't get into in a lot of detail previously that we're going to explore as we get into some of our lessons where we do the actual demonstrations. Now, beyond using feasible successors, we can also bind the EIGRP query domain by using that stub routing feature. So let's say, for example, we're doing some sort of DMVPN on the spokes. We would typically set those as stub routers and say that when the hub needs to do a convergence event, don't ask the spokes about them or about whatever convergence event it is, because they're only connected to their directly connected prefixes. There's no reason to go to a spoke router to identify prefixes that might exist beyond the hub router, if that makes sense. Okay? So there may be exceptions to that rule. There may be instances where we might want to leak out routes, if you will, or we might want to limit the scope of our query scoping, if you will. And we can do that by using leak maps. We did talk about that a little bit as well, to allow specific routes that the hub can do queries about, but not for every individual prefix. So even in that design, we have the ability to it's not an all or nothing scenario, I guess is what I'm trying to say. We're not limited to doing all querying or all query binding or domain scoping. We can actually configure some exceptions to that particular rule by using those leak maps. All right. The last thing that we see here, obviously, is the summarization. Everybody here is very well aware of what summarization involves. Maybe I give you a default route. Maybe I send you a query later. You might send a reply back to me and say, my only match is the /0 route. I don't have a match for any other particular destination. So that terminates that query domain from that perspective. We didn't necessarily configure that peer as a stub router, but we limited the scope of the query by essentially saying, you know what, the only route that I have is a default route. As a stub router, that's probably all that's necessary. As such, if you ask me about a prefix, I'm just going to simply tell you I don't have that prefix or I'm not aware of that prefix. So in the terms of configuration in EIGRP, we talked about all three of these options. There's really nothing else to say beyond what we talked about in those previous lessons for optimizing event propagation. But there are some other features that we haven't talked about, which we're going to get into more detail in the next couple of lessons as we go through the next few actual practical applications. All right. So propagation, event propagation, the ability for EIGRP to self-heal depends on the engineering design, the EIGRP design. Engineer in a feasible successor so that you have a backup route, and in the case of very specific topology designs, make sure you engineer some sort of query domain to shrink that query domain to reduce the overall convergence time. Okay. Now, in the case of OSPF, it does get a little bit more difficult. All right, so let me go put in a section here for OSPF. All right, in this case, event propagation is bounded primarily, not always, but it is bounded by the OSPF area. All right. The only exception to that would be if we have some sort of external domain that we're bringing into OSPF. In that case, it's going to be bounded by what we do on the ASBR. But for the most part, most of the kind of the efficiency that we gain in event propagation in OSPF is going to be based on the area. Okay. Okay. Now, what does that mean? All right, if I have less routers in the area, for example, less routers in an area, then we effectively reduces the overall change effect, if you will, because we have fewer routers that need to see that information. Remember, everybody within an area has to essentially agree on the overall topology. If they don't agree, then they're not going to be able to communicate. They're not going to be able to converge. Now, there is a little asterisk next to this particular statement because by default, OSPF does not really limit the flooding of LSAs beyond the area when it's doing that conversion from type 1 and type 2 to type 3. That's something that has to be manually configured within the ABR. Otherwise, if I have 1,000 type 1s in area 1, I'm going to end up with 1,000 type 3s in area 2 and area 0 and so on. All right, so how do we optimize this overall? We can optimize OSPF by using areas, smaller areas, I should say, and special area types. All right, we can also run something called incremental SPF or ISPF. That's something we hadn't talked about to this point, which we'll talk about. We can do something called prefix suppression. We did talk a little bit about prefix suppression when we were talking about things like the router bit and how do we set the router bit for a particular prefix that's coming in from an external domain and so on. Is this particular ABR going to suppress that prefix or not? We'll get into that in more detail again later on. And then we also have something else that we haven't talked about with OSPF, which is the SPF and LSA, throttling, and pacing timers. All right, so that's definitely something that we want to talk about in more detail. We'll get a little bit of an introduction to that in this lesson, but again, we'll get into that in a lot more detail in one of our future lessons. But it is a way for us to essentially identify how often I might propagate a particular event. Maybe, for example, I might anticipate that there's going to be 4 or 5 different changes whenever there is a topology change. And rather than send out 4 or 5 different updates, I'm going to go ahead and wait for a planned period of time before I decide to advertise those particular updates out of, out to my peers and so on. So it's kind of like a group update concept where I'm sending updates as a group message as opposed to individual updates, over a short period of time. Maybe it increases the event propagation time, but it reduces the overall load on the router itself and subsequently on the other routers that I'm sending the information to, because they only have to run the SPF algorithm one time. They only have to process the information one time, if that makes sense. So we'll talk about that a little bit later, okay? Now, going back to the first option, less routers in the area. In the case where we have a minimum number of routers within an area, and we have, say, non-backbone areas, we're still going to have some sort of event propagation from an area border router in order to update the type 3 LSAs or to update the type 4s or the type 5s if we're talking about external prefixes, right? The type 5s are generated by the ASBR, the type 4s being generated by the ABR that's attached to the area that has the ASBR in it. So when we're trying to optimize OSPF, in essence, if it's done correctly, adding areas can help, especially if we create special area types, whether they're stubby or totally stubby or not so stubby, because the minimum number of routers that we have in the database means that we have less LSAs to actually propagate. Again, that would require that you have some sort of summaries configured on those ABRs. It doesn't happen automatically. All right. All right. So in optimizing OSPF, we did talk about a lot of design elements in our OSPF chapters. We certainly spent a lot of time talking about the different LSA types, talking about how we could design special area types. So again, I would recommend going back and reviewing that. And we're not going to get into that again this lesson or even the future lessons. We're going to focus our attention on things like incremental SPF, prefix suppression, and SPF and LSA throttling and pacing timers. I'll introduce some of those concepts in this lesson, and then we'll look at some of the specific configurations later on. Let's say I'm using a default route, for example. Maybe it's a special area type, and I'm using a default route to get everything I need. So the only change is maybe an update of the cost of that particular default route. Remember, a default route would inherit, if it happens to be a summary default route, would inherit the lowest cost of whatever routes are included as part of that summary, although a default route could be statically injected with just a static metric. Usually that's not going to change. It depends on whether it comes in as an OE1 or as an OE2 or ON1 or ON2 route, okay? So the idea in OSPF is that if we can make the SPF domain as small as possible by shrinking the areas, then when there is an event, we have to recalculate, based on that event. We're going to be doing that recalculation based on a lower number of overall LSAs. Now, going along with this feature is a feature that is relatively new in OSPF, and it's called Incremental SPF or ISPF. That's going to allow the routers that are within the same area, and this is actually something that kind of happens automatically. It's not really a very tunable feature within OSPF, but it's going to allow the routers within a similar area to only have to recalculate portions of the tree that are affected by whatever topology change might happen or occur, rather than having to recalculate the entire database. All right, now this is kind of a debated topic in OSPF, whether this actually really solves a problem or not. But if I go under the CLI, you don't see this by default, but I did want to pull up this router for this reason. If I do a show run all section OSPF, I might have to do a section router, but let's see if it shows up here. We do see a lot of these features. Yep, here it is. a lot of these features are disabled by default. No prefix suppression, no ISPF. So if you're going to run this basically on all the routers in the same area, they all need to run that command, but it's really, really simple. It's just config T, router OSPF 1, ISPF, right? You're just a feature that you turn on. You can see it's not even really a tunable feature. And it's supposed to really allow the routers that are in a common area to work with OSPF more efficiently and to handle event propagation more efficiently. All right? Based on what portion of the tree changes in that particular case, those routers then can decide, do I actually need to run a full SPF, or is it just going to be a portion of the tree? But in general, like I said, you would turn this on everywhere, and then the routers themselves will decide based on the topology of the network or based on the SPF graph, do I actually need to do a recalculation within my area? All right? Now, in this case, we're specifically talking about the difference between intra-area versus inter-area routing. All right? Keep in mind, with intra-area routing, we need to have a complete graph of the topology. We know all the link states. We take all of that information as an input to the SPF calculation, and then we output the shortest path tree. So in the case of OSPF, ISPF is basically saying that if a portion of the tree is not going to change, don't rerun SPF for that particular portion of the tree. So you can see why this would be kind of one of those things that people would argue may or may not have specific value. It would depend on your overall topology. What does the graph look like within the topology? I would argue, though, that there's really no detriment to running it. I haven't seen anything like that where, you know, it takes up more resources or it's just not as efficient. So in the case of this feature, it's kind of like, well, I guess I'm just going to go ahead and enable this feature and let OSPF do whatever it needs to do. I'm not sure what version of code this was introduced in. I know it's been around for some time, so most modern routers should support it. All right. I mean, when you look at OSPF, right? Typically, when you look at the limiting factor of OSPF convergence, it's not usually how long does it take to run the SPF algorithm. Because we're not dealing with databases that are massive. We're not dealing with, you know, internet-sized databases that BGP has to deal with. So this is why you probably haven't heard of this feature or haven't seen it implemented in your own topologies, because there's just there's no necessarily you know, guarantee. Excuse me. There's no guarantee on what kind of effect that really, a positive effect that would have in your topology. But the idea is we can just input the new changes, add the output, merge it into a tree that we already have, which is theoretically supposed to cut down eventually on the propagation and the calculation times. That's the idea anyway. So incremental OSPF, yes, it technically could solve some of the event propagation issues, but whether it's really realistic in a design, whether it's going to help you in a particular design or not, that is a debatable topic. All right? Although I don't know that there are too many people out there actually debating it. I'm just suggesting that it's not going to be the magic bullet, if you will, and solve issues. If you're having issues in your topology with reconvergence, there may be some other underlying issues that you have to deal with. Now, the other two options that we have, let's go back to the list here, are kind of interesting. Prefix suppression, SPF and LSA throttling, and pacing timers. These are pretty interesting topics. When we talk about prefix suppression, SPF and LSA throttling, and pacing times, again, most of these specific elements are going to be kind of unique to your topology, but these are pretty interesting options. The prefix suppression, for example, we actually did talk about this a little bit when we were talking about the type 7 LSAs to the type 5 LSA translations, and you know, what are kind of some of the potential problems that we can have with the forwarding address in the actual LSA advertisement or the actual link state advertisement. And we did talk about that when we were talking about the routing bit and identifying who's going to propagate specific prefixes and so on. But in OSPF, as we know, the larger the database, the longer it's going to take us to flood that database, the longer it's going to take us to actually run shortest path first, right? So the idea is by shrinking the network into areas, that means we're cutting down on that flooding domain. We can also introduce the ability to do summarization, where we're actually summarizing the topology. We're not necessarily summarizing the NLRI, meaning we're not summarizing the actual routes, but we're summarizing the overall topology. Now, one way we can cut down on the number of routes would be to say that on our transit links between the neighbors, we don't want to advertise those particular prefixes. It's not necessary, if I'm doing next hop routing, to necessarily understand what the transit prefixes are and have those in my database. That's not something that's required necessarily for me to be able to route. We've talked about that many times as well. It's certainly an option. We can inject those transit prefixes in the database, but it's not really going to gain us much from the overall routing perspective. All right. Now, we are going to come back to this actually in more detail when we talk about MPLS Layer 3 VPNs. Specifically, we're going to talk about the MPLS core network. And we know, maybe from your experience or dealing with MPLS in the past, that the core is normally, the routers in the core don't need to know the routes to each other's transit links because we're using MPLS for forwarding decisions. And we're mainly concerned about exchanging network layer reachability information for customer prefixes. All right. We only need to know essentially, in essence, with MPLS Layer 3 VPN, how do I route to the loopbacks? Then I'm going to use the MPLS labels in order to reach the egress PE routers based on the MPLS tunnels towards the actual loopback interface addresses. But specifically in the case of OSPF, there is actually a command that we implement. It's not going to be at the global level. In the global routing process, it's going to be a link level command, which is going to be the IP OSPF Prefix Suppression command. It says, hey, when I generate a router LSA, which is a type 1 LSA, I actually want to include the IP address of that link in the description of the LSA or possibly exclude it. All right. So do I want to include maybe that link as a stub network? Or do I want to describe the point-to-point adjacency that's going to the other routers? Maybe it's not necessary. Maybe I don't need to include that information. That's going to allow me then to optimize the event propagation by minimizing the amount of information that we actually have to propagate. So if I have, say, for example, 10,000 routes versus 50 routes, obviously it's going to take a lot less time to advertise 50 routes because it's less intensive. The LSAs are going to be smaller that I need to actually advertise to the peers. All right. I think it kind of makes sense for you guys, right? Now, when we actually do the advertisement of the LSAs, based on the LSA flooding procedure, and then we run the SPF calculation, there are some configurable timers that we can set on the router to say when is that change happening, and then how long am I going to wait before I tell all of the other routers about that particular change, or basically how long am I going to wait before I propagate a particular event. And that's when we're talking about this SPF and LSA throttling and pacing timers. All right. Now we're just introducing these concepts in this lesson, but as we go through the last 3 lessons of this section, we're going to obviously look at the specifics and look at how these things look in the real world. All right. At least from a configuration standpoint. Now I could say on the reverse side, right? Say once I receive the event propagation and someone sends me a new LSA, for example, I make the decision as to whether or not I need to recalculate or reconverge. How long should I wait before I actually run the SPF algorithm, right? These are considered to be the pacing and throttling timers. All right. Now, typically, I would want to change this information. If I need to react to the topology change immediately, then I would set the LSA pacing time to be a minimal value. If I have to, if I have the ability to wait, for example, I might increase that pacing time. This is going to be done under the OSPF process. Again, if I go back to my router here and I do a show run all pipe section OSPF, what I'm looking for here in this particular case is I'm looking for LSA pacing. Let's see, timers pacing, here we go. So we can see we have several different options for throttling and pacing LSAs. Now, again, we're not going to get into the details of this specifically in this lesson. These are the default values that exist. By the way, using the show run all is very, very useful on the lab exam, because oftentimes you're trying to figure out something that you're configuring, but it's not going to show up in the show run because it's got a default configuration. So you're going to use something like the LSA flooding timers to manipulate that. All right, so pretty much all of the options that we have for generating and running SPF, this is going to be part of the sub-configuration under the OSPF process. Now, if you were to go to the actual documentation, let me see if I can find this here. Let's do the OSPF configuration guide. And let's see. Let me actually do the 2018 one. It probably won't make much of a difference, but let's go ahead and get the latest version. And I'm going to look for specifically under the timers, packet pacing and timers, and see if I have the table here. I really need the command reference. I do recommend taking a look at this. This is obviously something that we're going to be taking a look at in a lot more detail later on, because there are some best practice standards that you should follow. But this is something that most people, when they're implementing OSPF, don't typically tune these timers. All right. Let's see. Flood pacing, which you're looking at here. This is going to allow you to control the inter-packet spacing between the consecutive link state updates or the packets in an OSPF transmission queue, and it's going to allow us to modify that value. Let me see if I can pull up the OSPF command reference, because they have a really good description. I was looking at this earlier when I was preparing here. Let's see if this is the right document. Let me pause the video real quick. Good. All right, so I've got it here. So it says here for the usage guidelines, configure OSPF flood pacing timers, which allow you to control inter-packet spacing between consecutive link state update packets in the OSPF transmission queue. This command allows you to control the rate at which LSA updates occur, so that high CPU or buffer utilization can occur when an area is flooded with a very large number of LSAs that can be reduced. All right, so the default setting for OSPF packet pacing timers are suitable for the majority of OSPF implementations. Do not change the packet pacing timers unless all other options to meet the OSPF packet flooding requirements have been exhausted. All right, but you can understand what this is doing in this particular case. It's saying, okay, your OSPF network is too large to begin with. You're trying to generate LSAs in order to tell other neighbors, but when you do that, you spike the CPU and then you don't have enough headroom to run the SPF calculation at the same time. So this is one of those things where it's kind of like a last-ditch effort, if you will. There's obviously probably in this particular case other issues in your design that you need to change, that require you to change the pacing timers as maybe a stopgap measure. So you need to really kind of take a look at the overall topology design. Maybe your OSPF areas are too large, or your overall architecture, your spine and leaf architecture is not implemented correctly. Okay. The point of this is that I would recommend, in this particular case, look at the command reference specifically for the timers themselves, right? And like I said, in this document here, the configuration guide, we see the different timers that are available, which starts right, let's see, here I think I saw a list. Yeah, packet pacing timers, retransmission timers, group packet pacing time. You know, in my experience as practically as an engineer implementing OSPF, I've never had to adjust these values. And I would highly doubt that this would be something that you would have to do on the exam. But again, these are maybe tools that you can use in the event that you have a poor design. All right. We also have timers for LSA arrival. So let me go back to the other document here. Right here, LSA arrival. Let's see, right here. The value of timers LSA arrival, timers throttle LSA all. So we have an option here that says, okay, in this particular example, we're gonna do OSPF LSA throttling so that the start interval is 200 milliseconds, the hold interval is 10,000 milliseconds, the maximum interval time is 45,000 milliseconds. What is the overall objective of this? Well, again, it's not something that you necessarily need to know in detail, but in this particular case, it allows us to control the minimum interval that we have for accepting the same LSA, you know, based on information that's contained within the LSA, for example, the LSA identifier type, advertising router, and so on. We have another one called the timers pacing LSA group, and let me see if I can pull that one up. LSA-group, there we go. These are the ones I was actually looking at. There's arrival, pacing. These are the ones that I was recommending that you take a look at. All the ones under timers, obviously. Let's see here. This command allows you to control the rate at which LSA updates occur so that high CPU or buffer utilization that can occur when the area is flooded with a very large number of LSAs can be reduced. The default setting of OSPF packet pacing timers are suitable for the majority, blah, blah, blah. Specifically, do not change the timers, etc. Specifically, network operators should prefer things like summarization, stub area usage, queue timing, and buffer tuning before changing the flooding timers. There are no guidelines for changing the timer values. Each OSPF deployment is unique. All right, so how does this work? Cisco iOS software groups the specific periodic refresh of LSAs to improve the LSA packing density for the refreshes in the topology, meaning that if I'm getting, and by the way, if I set a smaller time here, that means I'm going to end up having more LSAs. So the idea here is that if there's a bunch of people that flood information to me, and then need to in turn pass that information on to the rest of the network, I have two choices, right? I could either flood them individually as I receive them, or I could try to group them together and then send those changes at once. Understanding, of course, where the effect of one versus the other, whether or not it's going to allow me to decrease the overall knowledge of the topology changes or increase the knowledge of the topology changes, if that makes sense. All right? And that's, again, something that we need to be concerned with, right? In our overall design, what is the objective of what we're trying to accomplish? it's a trade-off, right? Efficiency for the ability for the router to run, propagate information or calculate information and so on. So if I have a large group pacing timer, I'm trying to batch essentially the updates. So if we set that timer to a large value, we're going to increase the overall event propagation time because people are not going to be able to identify those changes necessarily quickly, but it's going to require less overhead, if you will. All right, so let's say I have, for example, 10,000 different LSAs. If I decrease the pacing interval, it might benefit me from a propagation and understanding perspective, but it might increase the utilization of the CPU and memory. All right, if you have a really small database, increasing that pacing timer could benefit you slightly, but it's really more of leaving it at the default and looking at other design elements to make it a little bit more efficient. All right, and there's other timers. You got timer pacing retransmission. If a link gets dropped, for example, we need to retransmit. There's an option for that one. There are options for SPF throttling and so on. Let's say, for example, throttle. Let me see if that was in the list here. There we go. Either one of these. I'll look at this one first. Timer throttle SPF. All right. So it says here, turn on the OSPF throttling. Use timers throttle SPF command to the appropriate configuration. It says usage guidelines. The first wait interval between SPF calculations is the amount of time in milliseconds specified by the SPF start argument. Each consecutive wait interval is 2 times the current hold level in milliseconds until the wait time reaches the maximum time as specified by SPF max wait. All right. Well, that describes the command. It doesn't really give us a use case. But let's say, for example, I have the start SPF, right? Well, there's 3 values in this configuration. Let me look at scroll up here. We see the 3 values there. You've got the SPF start, the SPF hold, and the SPF wait. Now it says for SPF start, the initial delay to schedule an SPF calculation after a topology change, anywhere from 1 to 600,000 milliseconds. Minimum hold time is the SPF hold between consecutive calculations, and then the maximum wait time between 2 consecutive calculations, and so on. So the first one that we see here is really just the initial delay to schedule the calculation. The default is 5,000 milliseconds. So this is where we say, we kind of saw this in the previous section, is that one of the limitations was that one of the routers reacted to, say, a BFD event, and it sent a flood event to the other router. But it wasn't until 5 seconds later, that 5,000 millisecond time, that they actually allowed the calculation or the start of the SPF calculation. Because the idea is that if one LSA comes in, it's likely that we're going to have multiple LSAs coming in, so let's go ahead and delay that start time. I think one of you guys was actually mentioning running into this situation with the BFD timers and the LSA propagation timers not being synced up. I can't recall who was mentioning that, but all right. So if I end up running SPF immediately, as soon as the first one comes in, obviously the issue here is I could run into 2 seconds later, I get another update, I need to rerun the calculation again. So depending on whether you want to react immediately and then back off after that, that's up to you. That's where the SPF hold timer comes into play. So we get these options where we're trying to hit a very low convergence number, but we want to set these values so that they're optimal and whatever that optimization might be. So maybe we set the SPF start time to be basically the minimal value, and then we would start to back off for the subsequent runs of the calculation, of the SPF calculation if we need to. All right, so the hold time is here, it says is the minimum hold time between 2 consecutive calculations. And then what's the maximum wait time between 2 consecutive calculations, and so on. What is the goal of all of these configurations? I mean, ultimately the goal of all these configurations is to stop us from thrashing the CPU because topology changes keep coming in and so on. Now, if you design your topology correctly, using special area types, using summarization, you may not ever have to resort to these tools because the calculations are going to be limited, or the topology changes are going to be limited in scope based on a good OSPF design. All right? But if the topology is not designed correctly and I keep getting a bunch of different changes, I'm going to end up running the SPF algorithm over and over and over again. And every time I rerun it, I might come up with some sort of new calculation. Then I'm going to have to flood again because all that information is different. So we're trying to get to the point where we're adding extra redundancy in the network design, but it's not going to end up adding any more resiliency. All right. Where you interconnect the routers, whether or not you have a mesh design or it's a highly mesh design, you end up building in this redundancy, but from a propagation standpoint, from a convergence standpoint, there's just too many changes coming in at once and it becomes detrimental. All right. Now, the same is true, and we'll actually see some cases where we can get around this by trying to pre-calculate path changes and so on. We'll get into that in one of our examples a little bit later on. But outside of doing things like LFA for OSPF, which is basically that equivalent to what we call a feasible successor in EIGRP, then we get subject to these individual timers where we have to go through the modification of the timers themselves. So without getting too deep into these, take a look at the document, kind of scan through them. Probably something you'll never actually see in a production environment, but if you have a good OSPF design, but you know, you don't certainly need to memorize it. Just know that it exists, that you can do it, and understand that they exist in the command reference because you'll have that available to you to understand what the effects are. Now, in the case of BGP, let's go back to our document here. This is our last protocol for the evening. In the case of BGP, BGP as a protocol works obviously a lot differently than your standard IGPs. All right, so in essence, BGP is really just an unbounded protocol. In essence, BGP is unbounded. All right. Now, that doesn't mean that we can't optimize BGP in some way, but most of the optimizations are going to be related to TCP rather than to the protocol itself. So maybe we use some sort of jumbo MTU, maybe we use a larger TCP maximum segment size, maybe a larger TCP window size, or maybe do some sort of like TCP selective acknowledgements, right? Again, because BGP relies so heavily on TCP as its transport, those are really our only options with regard to manipulating those values. All right. So if we're talking about event propagation in BGP, we talk about effectively tuning BGP based on BGP or TCP attributes. All right. Now, if I have a full BGP feed, maybe I'm sending a full BGP feed to multiple peers. Somebody somewhere on the internet is going to be sending some sort of recalculation. So it's actually pretty common in BGP to see updates constantly being sent. It's just kind of the nature of BGP, if you will. But if we think about actually optimizing BGP, we need to identify how we're going to optimize the actual transmission of those updates. All right, because BGP doesn't use its own transport, it uses TCP. We're limited in that regard to optimizing through TCP. All right. So things like increasing the MTU, for example, to a jumbo MTU, maybe 9216 or 9000 bytes. That means that when I go to actually send a BGP update, I can pack more information into the update into an individual packet. So instead of having to send you 5,000 update messages about all the routes, I might be able to send you maybe only 500 messages about all the routes. And depending on how much the actual effective payload is that I have within that TCP segment, will depend on how much information I can pack into that datagram, right? The same could be true, for example, for what the actual usable payload is. What is the maximum segment size for an individual packet? You know, what is the window size, right? In TCP windowing, we're talking about how many bytes of information can I send you before I expect to receive an acknowledgement, for example, right? How many bytes of information do I send you? A larger window size means effectively lower overhead because I only have to send acknowledgements every once in a while as opposed to every single datagram. All right. If you do need to send me an acknowledgement, send them sequentially, right? Or maybe not. Maybe I can say, let's go ahead and do a selective acknowledgement where I can acknowledge out of order. Can acknowledge some datagrams or acknowledge other datagrams. If I were to send you, for example, packets 1, 2, and 3, with selective acknowledgement off, you could actually acknowledge 1 before you acknowledge 2 or 3, or vice versa. You could acknowledge 2 before you acknowledge 1 and 3. Maybe something got dropped, maybe something got corrupted. I can go ahead and skip that. I'll acknowledge 2 and 3, and then you'll maybe retransmit 1. All right. So when it comes to optimizing BGP, we talk about optimizations of TCP. We talk about QoS, other things that affect things like the buffers and the routers and so on. Just keep in mind that in the case of BGP, it is an application. It's TCP based, so very much like a web server. I would maybe go into Apache and set different TCP optimizations on the web server to allow for larger web page downloads or other components, something like that, to make the web application effectively work more efficiently. So if we look at this from a router's perspective, if I did a show run all TCP, we don't have anything configured, but I can include TCP. We can see that there are many, many different options with manipulating TCP. We can see selected ACK. Let me see, where's selected ACK? There's the default window size. There's the TCP MSS. Delayed ACK is turned on by default. I believe selective ACK is turned off. Let me run that again. Let's see. Yeah, right here. No IP TCP selective acknowledgement. So that may be something that you turn on just to make BGP a little bit more efficient. I'm not going to suggest that that is a best practice standard. Again, I've never done that in a production environment because these would be things that you might choose to implement if you see certain symptoms and so on. But usually we're not going to worry about that. So the default window size in this case is 4128. It's pretty small. Assuming that we're talking about some sort of jumbo MTU, we can see that actually if we did a Wireshark capture. I don't have anything configured right now, so I can't. But we could see that actually if we have routers that are trying to establish a BGP peering. When they go through the TCP three-way handshake, they're going to do that MTU discovery, and they're going to identify what the maximum segment size is for that particular session. All right. Maybe when we do our next lab, I will go through and kind of demonstrate that. Just do a filter on BGP 179 and take a look at what that configuration might look like. We could change the values, right? In the three-way handshake, we can see when we're starting the session, we send a SYN over, and inside that SYN, we're going to say a maximum segment size is whatever. But the idea is that we do have the option of manipulating these values. Remember, you've got an MTU value. Maybe we set the MTU value to 9216, but you got your 20-byte IP header, you got your 20-byte TCP header, you got your maximum segment size. So that's going to end up being something like 9176 or something like that, which is what we'll end up negotiating in the BGP packet. So we'll see. I'll try to. I would show it to you right now, but I don't have any of my routers configured, and I don't want to take too much time doing that. But if I send that acknowledge or SYN, the other router is going to reply with an acknowledgement to say, hey, I agree that the MSS should be 9176. So that, what does that mean from an update perspective? It means that when we go to send out an update message, and that update message is large, we're going to be able to fit more updates inside that individual packet itself. All right. In order for me to be able to demonstrate that, I'd have to probably run some sort of script. I actually have a script that I had planned on using. I'm going to use it the next time around. This is a script that I got online that generates thousands of loopbacks. Well, as many loopbacks as you want on your router to generate prefixes for BGP. So next time we go through the process on our configuration, I'll probably do that just to show you what I'm talking about right here. All right. The idea is that, and I think you guys understand, if I'm going to shut down BGP, create all these loopbacks, these thousands of routes, redistribute connected into BGP, obviously I'm generating essentially a large BGP database, relatively large, certainly over 1,500 bytes. Do I end up sending all that information in one segment, or do I have to encapsulate it in multiple segments? All right, and we can optimize BGP in that regard. It's no different than adjusting the maximum segment size on an interface, you know, in any other option. All right. Now, if you look at under the BGP process, some of the default options. For example, one of the defaults under the BGP process is BGP transport path MTU discovery. If we increase the MTU of the effective path, BGP is going to be able to automatically deduce that with that feature enabled. All right. Now we're going to talk about MTU. We'll talk about fragmentation when we look at some of the other stuff when we do MPLS. But if the application, in this case BGP as an application, is running path MTU discovery and you're not blocking ICMP unreachables, you'll be able to discover that information and build your datagrams appropriately based on that information. Okay? I'm very curious to see, I got this script online, and I'm very curious to see if it actually works, because I want to save it for you guys. It's kind of an interesting TCL shell. Let me, before I run this script, let me go back and see what I'm supposed to type to execute it. It looks like I am supposed to, there. It looks like I'm supposed to type generate loopbacks. So let me see if this actually works. I have no idea if this works. I just grabbed it online. And let's see, generate loopbacks. And let's just do 1,000 of them. Might crash my router. Actually looks like it might have worked. Good, I'm excited to use this the next time we do our next lesson and we need a bunch of routes to add to the topology. Might take a while. I'll let that run. All right. Basically, what I was trying to do is figure out how to generate a whole bunch of networks to demonstrate the size of the database, if you will, for BGP in the updates. But we'll get into that a little bit later on. Okay. If you're dealing with BGP, this might take actually very long, because it's only on 42. I think I did too many. All right. Yep. It's probably going to take too long. Probably shouldn't have done 1,000, but it definitely looks like it's creating them. But anyway, just to wrap up our lesson for today. So increasing the MTU for as an example, in the transit path is a side effect, would generate the side effect of optimizing BGP because we're able to send more information in an individual update rather than having to send multiple updates at a time, right? And you get the idea. The takeaway from a BGP perspective, though, is that the optimization doesn't occur in the application. It occurs in the transport, the TCP transport. That's how we optimize BGP, okay? All right, so we'll go ahead and wrap up this lesson, and we'll get into the specifics. It looks like I probably should have chosen maybe 50 loopbacks because we're only on number 70 right now. Anyway, I'm going to kill that process. It does look like the script works, so I'll save the script in tonight's folder for tonight's lesson. Let me kill the routers here so that I get my CPU back. And what we're going to do in our next lesson is we're going to go back to routing protocol failure detection, where we're going to take a look at things like BFD and so on, and actually look at some configurations. All right, guys? So it's going to be this week, most likely Thursday. I'll be in touch with you guys, and we'll see you guys in the next lesson.